Today we're going to be looking at the idea of growing or decaying exponentially, specifically money. We all enjoy money. Let's see how compound interest works. And let's see how we can use logarithms and natural logs to solve exponential problems. So the beginning one, the exercise one here, if we're looking at the idea that if you deposit $400, right here, $400, and a 5% interest rate, and it says that you're going to get 5% interest per year. In A, it says how much will a savings account increase over that year. So remember that percents we always write as decimals, so 0.05. So we're going to get 400 times 0.05, and if you have a calculator, that's $20. And so if you have $20 and you started with 400, you're going to get 400 plus 20, and so we're going to get at the end of the year $420. So it says, by what single number could have you multiplied the 400 by in order to calculate part B? So this is the idea that we've talked about, that you really had 100% of your money and you added 5% on. So you could have done 100 times 1.05 equals 420. And again, that 100% includes the amount that you already started with, and that 5% is the amount that you're adding on to the original amount, or the amount that you have. So we're not going to do this, but how could you determine that? Well, you could keep going 420, that's year 1 times 1.05, and you could get 441. And you could keep multiplying by that. Well, if I'm going to do 400 times 1.05 times 1.05, that's really just saying 1.05 to the second. Again, that's first year, second year. So if I want to 10 years, I'm going to do 400 times 1.05 raised to the 10th, and that's going to give us 651.56. So give the equation for the number of years since this. So we're going to get S of t to equal the amount that we started with times the interest rate raised to the t. And I know it says use a table. I want to go right into logs here. So if we're asking for how much it doubles, well, 400 doubled is 800. We want to know how long it's going to take to double. Well, we have to get the exponent and the base alone. So I've got to divide by 400 here. We get 2 to equal 1.05 raised to the t. And again, the variable that I'm looking for is in the exponent, and therefore we are going to use logs. So I'm going to take the logarithm of both sides. Remember, when you take that, this t comes out. So I'm going to get log of 2 equals t log of 1.05. Well, the t is almost alone. We solved these last class. Divide by log of 1.05. Divide by log of 1.05. And you're going to get t to equal 14.21 years. And you'll notice the interesting thing here, that when you double something, or however much you want to multiply it by, this 800 divided by 400, no matter what the initial amount was, this will always give us 2. And therefore, no matter what you start with, it's always going to take 14.21 years for your money to double if the interest rate was 5%. And you could go throughout and do any of the other interest rates. But it does not matter with how much money you started with. It's going to always take the same amount of time to double or triple, or if we're declining, halve, no matter what the starting value is, as long as we know the rate at which it's increasing or decreasing. So we're always going to be able to say this. And this portion here uses different terminology. We usually use y equals p, parentheses, 1 plus r to the t. That's a t. Get that to look correct. T, where y, where this is our starting amount, this is our rate, and this is the period of time. So try number 2, and then I want you to read this part and try that also, and I'll come back with the answers. And so hopefully you got these answers. We do have 1 plus 0.03 or 1.03, does not matter. And for the second part, we're looking at decreasing. Remember that decreasing is just 100% minus that, and so you should have these answers. Remember that you need to move the decimal place over 2 spots. And so therefore, again, how I usually write it is y equals p, the starting value, 1 minus r to the t, but it doesn't matter which variables you use. It's the same equation. So if we look here at exercise 4, a town is decreasing by 4% and started with 12,500. So you start with 12,500. We're decreasing by 4%, so 1 minus 0.04 raised to the 10. And you could have written that as 0.96. There's nothing wrong with that. The answer is 8,310. Moving on, we're going to look at number 5, and I would like you guys to try to create 2 equations. One with wind power, so we're going to look at wind power, and one with the gerbil. Notice that wind power is increasing at 4%. Its initial value was $20 per share. On the other hand, gerbil energy is crashing and losing $11 per share. Gives you what gerbil's energy per share was. So try that one. I know many of you do not have calculators, so we will not be doing B. We'll be doing that in class. So there are the 2 equations. If you have any questions, let me know. So we come to this idea of this nominal yearly interest rate. And if you guys have bank accounts or credit cards, hopefully you guys do not have credit cards, but if your parents have credit cards or anything that dealing with interest rates, good or bad, gaining or losing money, we have this idea of nominal interest rates. So if we look at this exercise number 6, a person invests $500 in an account that earns a nominal yearly interest rate of 4%. How much would this investment be over 10 years if it was compounded once per year? Well, we already know how to do that. That's 500 times 1.04 raised to the 10. And we know that answer to be 740.7, 40.12. Let's just rewrite that. But what banks do is they say, hey, instead of giving you interest just at the end of the year, we're going to give you interest throughout the year. So if we say that it was applied 4 times per year quarterly, why would it not make sense to multiply by 1.04 each quarter? Well, if you think about that, if it's each quarter, you're going to get that 4 times per year. You're going to get 1.04 times 1.04 times 1.04 times 1.04. That's going to give you way more than 4%. You're going to get 4% each quarter to give you over 16%. And so you can't do that. So if it was you're earning 4% per year, how much would you earn each quarter? Well, it's going to be 4%. Quarters are 4. You're going to earn 1% per quarter. And so therefore, if I'm going to earn 1% per quarter, then I'm really earning, so if we take this, $500, we're going to earn 1.01 per quarter, but there's 4 quarters in a year, so I'm going to really raise that to the 4th. And so that's the equation we can look at. Now, let's look at how we got that. We got our starting value. We know that we're adding, so we're going to do 1 plus. I knew our interest rate was 4, but I divided it by the number of times it was compounded. So we did 4%, and we divided it by 4 because it was compounded 4 times. I raised that to the number of times it was compounded. Clear that up for you. Raise it to the number of times it was compounded times, and you could do this, if it was 2 years, it would have been compounded 8 times, so times t. So I took our starting value, how much we deposited in, I took our rate, I divided it by the number of times it was compounded, and then raised it to the number of times it was compounded, times the time period, the number of years that we have. And so, just so you guys know what it would be, and I guess I did not read this, it would be worth after 10 years, so I would have to do it times 10 there. So please note that. I needed to put it times 10 because it was after 10 years. This would give us 744.43. Now notice that because it was compounded quarterly, we do gain a little more interest. The difference between compounded once a year versus compounded quarterly does gain us over 10 years over $4, which if you added a couple zeros on there, that's appreciative there. So the pattern's fairly straightforward. For a shorter compounding period, we get to apply interest more often at a lower rate, therefore getting more money. And this is the equation I just talked about. A equals the amount that was invested times 1 plus R, the nominal yearly rate, divided by the number of times compounded, and to the n times t. This is just quarterly, so you're going to take 0.05 and divide it by 4, monthly 0.05 and divide it by 12, or daily 0.05 and divide it by 365. Those are just the simple ones. And again, we're trying to pound this in your head. This is in R. The equation again. The last thing that we're going to look at is this idea of continuous compounding interest. And this is where the letter E, the number E, comes into play. We found out from last couple classes ago that the E is the rate at which you compound something to a very high N value. And so this right here is our rate, the E is. So instead of doing 1 plus R over N to the NT, this we're just saying is E. So we're doing P times E to the RT. And what we're going to do here is, this is nice, is that the R value, if it's increasing, is just the R value, 0.02, 0.05, 0.10. If it's decreasing, it's just negative, which is a nice thing. You don't need to do 1 plus or 1 minus, just whether it's a positive or negative R value. So if it's continuous, whenever you see continuous, and this is key, you've got to use E. So write an equation for 350 at a 2% interest rate. You're going to get P equals, or A equals 350 E to the, you don't really need the parentheses there, I don't know why I did that, 0.02 T. And so how much would that investment be after 20 years? The T is 20. 350 E to the 0.02 times 20, and you do that right in your calculator. And the answer is 522.14. Now, again, where do logs and natural logs come into play? Right here. Algebraically determine the time it will take the investment to reach $400. This specific investment. So we have 350 E to the 0.02 T equals $400. Solve for T. Where is it? Oh, it's in the exponent. What a surprise, we're in the logs unit. So we've got to get E to the 0.0 T by itself. So we're going to divide. To get E to the 0.02 T, just divided by 350. And now we have an E. We learned before. We're going to take the natural log of it. So I need to take ln of 400 divided by 350 equals the ln of E to the 0.02 T. What happens? We know the L and the E are inverses, so we're left with ln of 400 over 350, you can simplify that, that's fine, equals 0.02 T. Why? That's what's left in the exponent. The last thing to do to get T by itself is divide by 0.02, not T, 0.02, divide by 0.02. You use your calculator, you use the alpha y equals enter to get the fractions, and we find T to equal 6.7 years. Round to the nearest tenth, we're done. This is where using logs and natural logs are useful. The effective annual rate is just asking what would the overall rate be that it increases over one full year. Well, how do we get that? You're going to go E to the 0.02, and that's going to give us the rate at which it's changing, which is 1.020201. And if we take that into a percent, you're going to get 2 0.02%. See you in class.